All right, Professor Garb here, lesson 3.3. Here we are. So, first question asks us about average rate of change. Can the average rate of change of a function be constant? Yes or no. So, a line is a constant rate of change, and that's what we call slope. So if it wasn't a constant rate of change, let's say you're walking up a hill and that's the pace that you're going, or that's the speed that you're going at. If you go a little faster, then a little slower, then a little faster, then a little slower, then a little faster, that's no longer a line. But if we have the same vertical change of a horizontal change along the way, that means it's like we have our cruise control on, so that's the same rate of change. So we're going to select this guy, okay? So all lines have a constant rate of change. That's correct, otherwise it's not a line. If a function is increasing on a to b, okay, so this question talks about increasing and decreasing. So it says if a function is increasing on a to b, here's a, here's a, here's b, and decreasing from b to c, so we need a c here. So if it increases from a to b and then decreases from b to c, kind of like that, right? What can be said about the extrema of f on a to c? So local minimum at x equals b, I don't think that's a minimum. Local maximum, yep, right there. So I guess we could pick this guy over here, local maximum. So we know that has to be maximum because we go from increasing to decreasing, so it's got to be higher than a, and b has to be higher than a, and b has to be higher than c, and c has to be lower than that, so that makes sense. Moving on. How are the absolute maximum and minimum similar to or different to the local extrema? All right, so local and absolute. So absolute, that has to deal with everywhere. Okay, so that's like saying the world's lowest temperature ever recorded versus the lowest temperature ever recorded in Fargo, North Dakota, or a specific area, or a specific amount of time. Okay, so absolute is all time, everywhere. But local, it's like just a short defined period of time. So local, smaller span of time. So, for instance, you might have a function that looks like this. For a local period, that might be the local max, but the entire function, this might be the local max up here. Absolute max. That might be the absolute max, and that might be a local max. Okay, for this defined area, and that might be a local min right here, but this might be an absolute min down here. So that's what they're talking about there. Find the average rate of change over the interval. Okay. So the average rate of change, we have the function, which is f of x equals x squared minus 4x plus 8. Now the average rate of change over the interval -4 to 0. So we just need to find the amount of change and then divide by the length of the interval. Okay. So the average, I'm going to call that AROC, the average rate of change, and that's equal to the total change divided by the length of the interval. Okay, so in this case, the length of the interval is going to be 4, but we have to find out what that total change was, change from -4 to 0. So we'll try to put 0. 0 is easy to put in there. So if I put in 0 at the end here, I'm going to get 0 plus 8. So I'm at position 8, okay, when it comes to 0, but I have to try -4 and see what value that gives us. So we put -4 in there, and we're going to get 16. Careful, it's a minus there, so it's going to be plus 16 plus 8. So that's a larger number. So it's 32, that's 40. So it looks like we go from a 40 to an 8 over that 4-unit time span. So we went down 32 units from 40 to 8, and over 4 units of time. So it's an average rate. So you're losing 8 units per 1 unit time. So it's -8 per 1 unit time. All right. So typically average rate of change will be -8, down 8. All right. Moving on. Use this graph. We're trying to average rate of change from 0 to 5. So again, we're trying to find the AROC from 0 to 5. So the length of the interval. Okay, remember what that means? It's the change over the length of the interval. Okay, so the amount of change, we have to figure that out. The length of the interval is going to be 5. So now we're dividing by 5. So the average rate of change. Well, let's take a look. So we start at 0. 0 starts at 5. If you look on the graph over here. So if you look on the graph over here, you can see at 0 it's right at 5. And at 5, it looks like it's down at 1. So it goes from 5 to 1, which is down 4, okay, over 5. So it looks like a rate of change of -4/5. Okay, try -4 over 5 for that one. Now, here for number 6, it gives us values for f of x and g of x over here. Okay, so these are like y's, and these are our x values for both, and y values for 2 different functions, f and g. The average rate of change of g from 3 to 9. So we have to focus our eyes on the right section here. Now we're talking about g, so we're looking at this right-hand column right here, this right-hand column. So I'm looking from 3 to 9. So from 3 to 9, so that's a span of 6. So I know my denominator is going to be a 6. Okay, so at time 3, what is g of x? So at time 3, g of x is 5. Okay, and at time 9, g of x is 1. So I went from a 5 to a 1, which is down 4 over 6. And then you want to simplify that to down 2 over 3. So you simplify it to Löwit's forms. It's going to be -2 over 3. So that means it loses 2 units for every 3 units of time. That's what that means. So it's slope. It's a ratio. And it tells us how much change in how many units intervals of time. And that together is called the average rate of change. The next one here is the average rate of change from 0 to 4 on the graph. So we go from 0 to 4. So we know we're going from 0 to 4, so that's a change of 4 units of time. Now we're going from 0, so x equals 0, looking here, we're going up to see what the y value is. That's 5. And time 4 is going to be 2. So this part of our graph here is kind of irrelevant from 4 to 5 because it's not addressed in the question. So at time 4, it's going to be 2. So we're going from a 5 to a 2, which is down 3. So it's going to be the average rate of change, the AROC, average rate of change is going to be down 3 and over 4. Okay, moving on. So we have to check the boxes. Which of the following are true? So it could be more than one, so I have to keep that in mind. So we're talking about slope here. That's what the average rate of change is. So the average rate of change of a function over specified time is change in output over change in input. Yes. So what is slope? Okay, so it's basically change in y over change in x. This little triangle means change, and it's a delta, a Greek letter. So that is okay, and you know there's other pseudonyms for this. This is vertical over horizontal. So it's horizontal. So it's vertical change over horizontal change. We could say it that way too. Remember, this is also range. Y is also range. This is domain. So there's lots of ways of saying the same thing. So we look through these questions and see what they say. Average rate of change. Output over input change. Yes, it's like change in Y or change in X. If the average rate of change is the same at any two points of a function, then the function is a linear function. Yeah. Yeah, because the average rate, we said that a line has a constant rate of change. That's its slope. The average rate of change is another term for slope of a given interval. Yes, it is. Is another term for average rate of change is slope over given interval. It's right. And the average rate of change, no. So the only one that's false is the last one. So I'd pick those first three ones. Next one here. Let's see what they say, number 10. Okay. They say we're taking data from a chart. So they want to know, is the living wage of jobs in Rochester per 1,000. Okay, per 1,000 adults over a 5-year period. So they want to know the average rate of change from 1997 to 1999. So that's from 1997 to 1999. That's 2 years. So I know my time period is 2. I'm going to have to find the change in living wage during that time. So from 1997, it's $665. It's 1999 is $775. So that's a positive change of 110 over 2, and then we simplify that, it's going to be 55. So on average, it's 55, it's per 1,000. So 55,000 per year. So 55 units per year, and it's per 1,000. To chart shows living wage jobs. What's the number of jobs? Yeah. So that's the number of jobs per 1,000. So it's like 55 jobs per 1,000 people per year change. So I think 55 should work. What's the average rate of change in the number of living jobs from 1999 to 2001? Well, that denominator is also going to be the same 2 years because it's 1991 to 2001 right there. But it's from 99 to 2001, so it's 775 to 830. So it's going to be a smaller rate of change. You see how it's going up here, but by less amount each time. So it's going to be 25, it's going to be 55. So it's 55 for every 2. So we can't simplify that. So we're going to leave that as 55 over 2. I don't know whether the program's going to want a specific answer, but it would be 27.5. But I'd say 55 over 2 is a good answer. That means it goes, so the change is half as much. Because over this 2-year period, it changes 55 jobs per year, and here it changes 55 jobs for every 2 years, so the growth rate is less. So that means it's a flatter line going up. So see, this was a greater rate of change, this is a slower rate of change. Just so it looks like what it looks like graphically. Bicycle problem. Good, I like bicycles. It's gonna be fun here. On a bicycle, Nate rides for 5 hours and is 62 miles from her house. Oh, Natalie, sorry, not Nate, Natalie. After riding 10 hours, she is 122 miles away. What is Natalie's average rate during her trip? Well, we have 2 different times, 5 and 10. This must be a long bike ride. I like those. All right. So after 5 hours, she's 62 miles away. And after 10 hours, she is 122 miles away. So again, average rate of change is going to be AROC. So we know the change here is going to be 60. So she changes 60 miles or rides 60 miles during that 5-hour interval. So that means her average rate of change is 12 miles per hour. Okay, that's her average speed in that case. And number, we have to have time for one more in this video. Number 11. So we have a function, what was the average involving h. Okay, so you have to do the same thing but with h. So if we go from negative 1 to negative 1 plus h, the amount of change there in time is h, right? Because negative 1 and negative 1 are the same, so the only thing you're adding is h. So now I'm dividing by h. So it's the same problem but with letters instead of numbers. And in here, we have to put in h. So we have x squared plus 6x. We have to put in negative 1. So it's going to be 1 and then minus 6. 1 minus 6 is going to be negative 5. And the other one there is negative 1 plus h. So I have to square that one. That's going to be 1 minus 2h plus h squared. And the other, so it goes from there. So that's going to be h squared minus 2h plus 1. and then minus 5. So you're going to get h squared minus 2h minus 4 over h, and you have to simplify that down. I'll pick up